So in section 8.1, we introduced the topic of confidence intervals. And in section 2, we're specifically going to look at finding confidence intervals for a proportion. Okay, so there are a few criteria we have to have in order to complete this. We're using a sampling distribution. So we have to remember that the shape has to be normal. So we're using the same formula that we did in chapter 7, but Q is now representing the 1 minus P. So Q equals 1 minus P. So we still have to have that NP is greater than or equal to 10 and NQ is greater than or equal to 10 for it to be normal. The mean, which is the center, is mu sub P hat, which is the same as the population proportion. And then as n gets larger, the standard deviation gets smaller and can be found with our same standard deviation formula. Remember, this is also referred to as standard error. Okay. So first, we're going to estimate our parameter with our sample proportion, which we will then use to set up our sampling distribution, and then we'll find the interval that will contain a certain percentage of samples in the sampling distribution based on how confident we want to be. Excuse me. So our first example says, in a large bucket, there are many jelly beans. A student selects 100 jelly beans and gets 24 red beans. Construct the 90% confidence interval for the population proportion of red beans in the bucket. So first we need to calculate our mean and standard deviation. So we know that our mean is gonna be equal to our parameter. So P hat is gonna be equal to 24 over 100, which is 0.24. So our parameter is gonna be 0.24 as well. Okay. Next, we need to calculate our standard deviation, or our standard error. So the square root of 0.24 times 0.76 over 100 which is going to be 0.043. Okay. So when we construct our normal curve, remember 0.24 is going to be in the middle. And then what we now need is the critical value. This is it's something called Z star. So what we're gonna use is that table that I gave you guys. So at the bottom 2 lines of the table, one line is the Z star, and then the bottom line is the percent confident we want to be. So we want to be 90% confident. So we go to 90% on the bottom and we look for the value, which is going to be 1.645. So if we use that formula from the end of our section 1 notes, which means we take our P, which is 0.24, and we add and subtract our critical value, which is 1.645, times our standard error, or standard deviation, which in this case is 0.043, that's how we're going to get our confidence interval. So when we're looking at the normal distribution, if we want to contain the 90%, we go 1.645 away from our mean. And then the area we've shaded is our 90% confidence interval. So 1.645 times 0.043 is 0.071. So remember, this 0.071 is also called the margin of error. So when we do 0.24 minus 0.071, we get the lower value in our interval, which is 0.169, and then we do 0.24 plus 0.071, and we get the upper value, which is 0.311. So we can generalize our formula for a confidence interval, but it is derived from the process that we just did here. So what a confidence interval does is it estimates the population parameter and a margin of error that completes that interval. So we have a generalized formula where if we choose an SRS of size n from the population with a sample proportion of p hat, when n is large, the C% confidence interval is given by that formula, where Z star is a critical value, which is based on that table. And then we have our standard error formula for a proportion. So we are going to take a look at a few examples of this. Okay. So our first example says you wish to estimate with 80% confidence the percentage of smokers who consider themselves to be addicted to cigarettes. In a survey of 260 smokers, 15% stated they were addicted to cigarettes. Find the 80% confidence interval for the population proportion. So first we're going to start with p hat, which is going to be the 0.15. Because we know 15% stated they were addicted to cigarettes, and n is going to be our 260. So if we use the formula from above, we'll have p hat plus or minus our critical value times our standard error, and that's how we'll get our confidence interval. So p hat is 0.15 plus or minus. So using our table, we go to 80% as our confidence level, and we look, and our Z critical value is 1.282. Then we'll have 0.15 times 0.85 all over 260 underneath our square root. And remember, that second value, the plus or minus value, is our margin of error, which I'm just going to abbreviate MOE. So we'll have 0.15 plus or minus, and I'm going to do all of the multiplication in one step here. 0.028. So 0.15 minus 0.028 is 0.122, and 0.15 plus 0.028 is 0.178. The other thing we need to discuss is how we interpret a confidence interval, like how we would write a sentence summarizing what we find. So the way we start it is we say with, and then whatever percent confidence we did. So with 80% confidence the proportion of all smokers who are addicted is between 0.122 and 0.178. So the confidence level you look at determines the width of your interval. The more confident you want to be, the wider your interval will be. There is a way to do this on your calculator as well. So if you know your sample size and how many out of the sample are successes, you can calculate the confidence interval. So what we're going to do is we're going to go to stat and then over to tests and then one proportion z interval. So you're going to happily scroll all the way down to A on your calculator. So we have to fill out X, N, and our C level. So X is based off our P. So we want it to be 15%. So we need to figure out what 15% of 260 is, and that's going to be X, which is 39. N is going to be 260, and then our C level is the 0.80. And then we'll go down to calculate. And if we look, it then gives us our P hat in our interval. So the interval in the calculator is actually a little bit more accurate than the interval we calculated because they're going to go more decimal places. So you should get 0.12162, 0.17838. Now, if I round 3 decimal places like we chose to do, it's the exact same interval. So you can see how if I had rounded and done multiple steps when I calculated the margin of error, I could have gotten something that was a little bit more different by a decimal place than if I just do it all in one step. So we're going to try to limit the amount of rounding we do with our confidence intervals by trying to calculate our margin of error in one step. Let me know if you have any questions so far about confidence intervals.